Hello everyone and welcome to our 6th lecture in E274 and COE 197E. So we'll discuss inverse Z-transform as well as the unilateral Z-transform. I'll be discussing two methods for the inverse Z, the power series expansion method and the partial fraction expansion with table lookup method. And then we'll also show the unilateral Z-transform, which we will use to solve our discrete time system responses. The actual definition for our inverse Z-transform is defined as follows. Take note that here, we need to integrate x of z along a complex plane, and that requires contour integration, which will be tedious to solve. In this lecture, we'll discuss two mathematical techniques which will allow us to solve for the inverse transform without going through this definition. Our first method is the power series expansion. In this method, we need to represent our signal or our function in z as a proper rational expression. Here, if we divide the numerator by the denominator, we'll get a quotient in terms of z to the n or z to the minus n. And those terms will be the sum of the impulses of our actual time domain signal. Now for this method, we need to take note of the orders of terms. Now for a causal sequence, the polynomials must be arranged in decreasing powers of z before division. For an anti-causal sequence, the polynomials in z should be arranged in increasing powers of z. And it is not advised to use this method for a two-sided sequence, since we need to decompose it to its causal and anti-causal parts, which will also require another method, which is partial fraction expansion. Now let's get the inverse Z-transform of our example. Here we have a causal signal as shown by the ROC. So let's rearrange the terms in decreasing powers of z, which is already done here. So if we perform polynomial division, we'll get this particular quotient. And these terms are already the impulses in our time domain. So this one here is our value at n equals 0. The minus 4z to the minus 1 is negative 4 at n equals 1. This 10 here is at n equals 2, and so on. Unfortunately, the division does not end, so we don't have a closed form expression for our x of n using this particular method. If we want to get the anti-causal form, we just need to rearrange the terms in increasing orders of z, as shown here. We'll get a different quotient. The first term at negative 0.5z will occur at n equals negative 1, and 1.25z squared will be 1.25 at n equals negative 2, and so on, going to n equals negative infinity. Here we also do not have a closed form. Now this particular method offers a fast and effective way to get the actual samples. However, the disadvantage is that we cannot always get a closed form expression. The next method is the partial fraction expansion. For this method, our goal is to express our function as a linear combination of smaller functions with known inverse transforms. And we can do this because of the linearity property in our z-domain. In our lookup table, we can have three cases. We'll have real and distinct poles. We also have complex conjugate poles and multiple order poles. For our first case, we can rewrite the small x of z's as a sub case over 1 minus b sub case z to the minus 1. Now this particular form follows an exponential function in z, as shown here. We have the causal form and the anti-causal form. For our case 2, we have our complex conjugate poles. We can express our small x of z's as sum of two terms wherein the coefficients are also conjugates of each other, as well as the poles. And we can also express this as a cosine with the following parameters. We can also use the lookup table to determine the inverse transform of this particular case. So for our last case, we have multiple order poles. Here we need to separate our function into terms wherein the denominator has increasing multiplicities depending on the multiplicity of our pole. And the numerators a sub k can be determined using differentiation and cover-up method or by comparing coefficients and cross-multiplication. Now let's try to get the inverse Z transform of the following function using partial fraction expansion. Here we have two distinct and real poles. So we can separate them in two terms. We can either use cover-up method or cross-multiplication method to get a and b, which we can obtain easily. So the value of a equals 4 and b is equal to negative 3. And since there are no ROCs given, we have three possible cases. The first case is an anti-causal form. The second one is a causal form. And the third one is a two-sided form. For the anti-causal form, we can easily obtain this inverse transform, as well as for the causal and the two-sided form. For the two-sided sequence, the Z transform will only be guaranteed if the ROC is between 0.5 and 1, which means our second term should be causal, the first term should be the anti-causal. For our next example, we have this function, and by inspecting the denominator, we'll see that the poles are complex conjugates, and we'll have this particular form, similar to our case 2. And then we'll have this cosine function. Since we've already discussed the Z transform and the inverse Z transform, we can already use the indirect method to solve for the system responses of causal LTI systems. So once we have our LCCDE, we can transform the equation into the Z domain. And in the Z domain, we can already set our assumptions if we're looking for the natural response or the forced response or the other responses. And then we'll use partial fraction expansion with table lookup to get our y of n. Now the transform of our causal system is called the unilateral Z transform. Here we define our unilateral Z transform as the summation of our x of n multiplied to z to the minus n from n equals 0 to infinity. Some notes on the unilateral Z transform. Some sequences may be equal for n greater than 0, but differ for n less than 0, and still have the same x of z. Next, the ROC should always be at least the exterior of a circle, since the assumption here is causal. Next, all the properties of the two-sided Z transform can be used in our unilateral Z transform, except for the time-shifting property. And lastly, we'll incorporate the non-zero initial conditions for the unilateral Z transform. Now for the time-shifting property, we can have time delay or time advance. As you can see here, we still have the same form. However, for the unilateral Z, we'll add up some initial conditions for the time delay, as shown here. And for the time advance, we have these future conditions subtracted to our transform. Now let's try to solve this difference equation using the unilateral Z transform. Here we have our input as 0.5 to the n u of n, and we have these initial conditions. First, we can already transform the LCCDE into our Z domain, and using the time-shifting property, we'll incorporate the initial conditions for x of n minus 1, y of n minus 1, and y of n minus 2. Plugging in the values, we get this equation. And the next step is we need to group the same terms for the y of z, the x of z, and the initial condition terms. After rearranging, we'll get the following form. So we have this term with our x of z, which is also called the zero state response. And for the initial condition terms, we call them as the zero input response. Now the next step would be to perform partial fraction expansion and table lookup to determine the inverse transform. Here we'll get the zero state response as follows. And for the zero input, we'll also do the same. So we'll get our zero input as u of n. And adding them together, we'll get the total response. In our total response, we can already see the transient response denoted by the exponential signals and the steady state response denoted by the constant signal. And we can also see the force response, which is of the similar form of our input 0.5 to the n, u of n, and the natural response. In summary, we've discussed two methods to solve for the inverse z transform, which are the power series expansion and the partial fraction expansion with table lookup. And we've also discussed the unilateral z transform and how we can use it to solve the system responses in our causal LTI systems. For further reading, I'd recommend these following chapters in our references. That's it. Thanks for listening.